The power of the wind has been harnessed for centuries. The windmill is just one example. It used the wind to turn a millstone and grind grain into flour. So it was natural to think that the kinetic energy of wind might be used to generate electricity, even as far back as the first attempts in 1887. Today, both land-based and ocean-based wind turbines are playing an increasing role in generating electricity around the world. Denmark is now producing more than 25% of its electricity from wind. Wind power might be the easiest way to grasp the process of electrical generation, since the turbines are so plainly visible. At a wind farm, the turbines are those beautiful big propeller blades. They catch the wind and spin. This, in turn, spins the generator housed high atop the tower, and electricity is produced. NB Power buys electricity from 3 wind farms in New Brunswick. They're owned and operated by third-party companies. There's one at Lamec, 30 turbines, one near Bathurst, 33 turbines, and this facility outside Petitcodiac called Kent Hills, with 50 turbines. Kent Hills covers many hectares. It was built in phases between 2006 and 2010. 52 kilometers of roads had to be made just to service the turbines. It only takes a team of 3 people to operate the facility, although additional staff is brought in for maintenance on the turbines. Maintenance can include things like blade inspection and even a check on the roof deck of the turbine, if you don't mind heights. What makes for an effective wind turbine? How about a little science borrowed from the field of aviation? The blades you see here work much like aircraft wings. They're made from a carbon fiber composite designed to be high strength and low weight. Wind moves faster over one side of the blade than the other, creating a pressure difference and pushing the blade to one side. 3 blades around a central axis, all pushing in the same direction, and we get rotation. Sensors attached to the turbine turn the whole unit so that it constantly faces the wind. And the angle of the blades is automatically optimized for efficiency. Determining the amount of power available from the wind comes down to some math. The available power is 1/2 times the area covered by the blades, times the density of the air, times the wind speed cubed. This last part, wind speed cubed, is very important. Let's look at that formula again, but directly in relation to a wind turbine. The power available is 1/2 times the area covered by the blades, times the density of the air, times the wind speed cubed. The vital part here is the wind speed cubed. If the wind speed is doubled, then the amount of power in the wind is 8 times larger. That makes wind speed the single most important factor when determining where to build wind farms. The higher average wind speed locations in New Brunswick are shown on this map in orange to red. No coincidence that the 3 wind facilities are all found in red areas. Getting the turbines high above ground reduces interference from trees and other objects, resulting in faster, cleaner wind. The turbines at Kent Hills are 80 meters above the ground, so that the top of the blades reach 125 meters above the ground. After wind speed, the amount of power available from the wind most depends on the area covered by the turbine blades. This area is determined by the standard math formula, pi r squared. So when we double the length of the blades, we double the radius of the circle, but we quadruple the area of the circle. This also quadruples the amount of power available. Double the blade length, quadruple the power. That's why blade lengths are always increasing. The turbine blades at Kent Hills measure 45 meters each. Do they seem to spin slowly? Out at the tips, the blades are traveling at nearly 300 kilometers per hour. The blades are connected to gearboxes. These gears change according to the wind speed to ensure that the blades are always spinning at a constant 16 to 17 RPM, even in high winds. And the gears ensure that the generator spins at 3,600 RPM, or 60 cycles per second. When wind speeds exceed 80 kilometers per hour, the turbines are halted for safety. Each of the units at Kent Hills has a capacity to produce 3 megawatts of electricity, 150 megawatts for the whole facility. That would be about 3% of what is needed to power New Brunswick. So the great advantage of wind power is, 1, the fuel is completely free, and 2, there are no emissions or chemical pollutants. It might seem like the perfect fuel source, except there are drawbacks. Wind is completely uncontrollable, and while annual wind rates are consistent, short-term wind speeds can't be predicted, much more than a few days in advance. Industries and emergency services that run 24/7 can't fluctuate with the weather. By contrast, fossil fuels can be controlled, but are subject to price fluctuations and produce emissions like greenhouse gases, contributing to climate change and air pollutants. So while Kent Hills has a capacity of 150 megawatts, it rarely produces this amount of electricity. Typically, a land-based wind farm will produce only about 35% of its capacity over the course of a year. This is called its capacity factor. This output is steady from year to year, but unpredictable week to week. Nuclear or fossil fuel facilities typically run at 80% of their capacity or better. This low capacity factor results in wind power having a lower return on investment today. This is, in part, due to the fact that there is no cost associated with emitting greenhouse gases. And it means that facilities like Kent Hills have to be operated differently from conventional power stations. Most power plants respond to the demand for electricity and use more or less fuel. Wind farms respond to the supply of fuel. When there's wind, there's electricity. So wind farm technicians provide weekly output estimates based on the weather forecast as to how much electricity they expect to produce. These estimates are updated constantly. The system operator has to be sure that other power plants can step up their output during poor wind conditions and ease back generation when Kent Hills nears its output capacity. The power grid in New Brunswick is a sophisticated balancing act. What other challenges come with wind power? Our New Brunswick winters have to be factored in. Ice buildup on the blades is an issue for wind turbines, much like it is for airplanes. Ice disrupts the aerodynamics of the blades and can significantly decrease the amount of power that a turbine can produce. It can also be a hazard if ice is thrown off the blades at high speeds. Freezing rain forecasts are accounted for, and ice cameras on the turbines are used to detect ice buildup. Wind turbines are sometimes cited as a cause of bird deaths, but this has not been a problem at Kent Hills. Strict regulations and monitoring are required for modern wind farms. Much of the discussion around bird deaths and wind turbines comes from some of the early wind farm sites and technology. Much has been learned since those first installations about turbine siting and design to minimize the impact on birds. Wind turbine blades have a distinctive swoosh sound associated with them. Some people living near to wind facilities report the sound as annoying, and some associate it with a loss of sleep. Regulations are in place in most jurisdictions, that specify minimum setback distances from other buildings to prevent any adverse health effects from wind turbines. Changes to blade aerodynamics and internal gearing can also help reduce the noise levels. At many wind farms, the substation transformers now make more noise than the turning of the blades. Wind once powered the fastest means of transportation. It moved cargo around the world. For centuries, it processed grain and pumped water. Can it play a larger role in power generation in New Brunswick? It is a clean, costless fuel, but inherently unpredictable. Will it turn out that brilliant thinking by students like you will overcome the challenges of wind-powered electricity?